Welcome! In this session, we'll explore an interesting problem titled Number of Lines to Write String, which challenges us to calculate the number of lines needed to write a given string based on character widths. Stick around as we delve into the problem, analyze approaches, and derive an optimal solution. In this problem, we are given a string S consisting of lowercase English letters and an array widths of size 26. Each index in the widths array corresponds to a letter from A to Z, where the value at each index represents the width of that particular letter. Our task is to determine two things: first, the total number of lines required to write the string S, and second, the number of units of width used on the last line. Each line has a maximum width of 100 units. For example, if the width of a letter is 10 units and a line can hold up to 100 units, this means you can fit up to 10 such letters in one line. The input format specifies the constraints for widths in S, and the output is an array of two integers, the total number of lines and the width used on the last line. Now, let's consider the first example. Here, the widths array assigns a width of 10 units to every letter from A to Z, and the string S is the entire alphabet, A, B, C, D, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. To calculate the result, we determine the total width of the string, which is 10 units multiplied by 26 letters, giving us 260 units. Since each line can hold a maximum of 100 units, we split this total width across multiple lines. The first line accommodates the letters A to J, using exactly 100 units. The second line holds the letters K to T, again using 100 units. Finally, the third line contains the letters U to Z, using the remaining 60 units. Therefore, the output is 360, indicating 3 lines in total and 60 units used on the last line. In the second example, the width of letters varies. The widths array assigns 10 units to most letters but only 4 units to the letter A. The string S is bkda. To write this string, we calculate the width line by line. The first 9 letters, B, 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 C, 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 D, 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 have widths of 10 units each, summing to 90 units. These all fit on the first line. The remaining 3 letters, AAA, each have a width of 4 units, totaling 12 units, which fit entirely on the second line. This makes the output 2, 12, meaning 2 lines are required, and the last line uses 12 units of width. The third example demonstrates a case with smaller widths for the letters in the string. The widths array assigns specific values to the letters, such as 64H, 84E, 94L, and 640. The string S is hello. Adding up the widths of these letters gives 6 plus 8 plus 9 plus 9 plus 6, which totals 29 units. Since this total is well below the maximum width of 100 units, the entire string fits on a single line. Thus, the output is 129, indicating only one line is needed, and all 29 units are used on it. Finally, let's explore some edge cases. For instance, if the string consists of just one character, like A, and the width of A is 10, the output will be 110, as it fits entirely on one line. Another case is when all letters have equal widths, such as 5 units each, and the string is A, B, C, D, E, F. Here, the total width of the string is 30 units, which also fits on a single line, so the output is 130. If a string exactly fills one line, like A, B, C, D, F, G, H, I, J with each letter 10 units wide, the output would be 100. On the other hand, if the string spans multiple lines, like Z, 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 Z with each Z having a width of 10 units, the number of lines will depend on how the widths accumulate past 100 units. These examples highlight the importance of efficiently iterating through the string to calculate cumulative widths and determining when to start a new line. To solve this problem, we considered 2 primary approaches. The first is the brute force approach, which involves iterating through the string one character at a time. For each character, we calculate its width and keep adding it to the current line's width. If the total width exceeds the limit of 100 units, we start a new line, increment the line count, and reset the width for the new line. While this method is straightforward and works well within the given constraints, it does involve repeated arithmetic operations for every character, which could be seen as redundant. Although it has a time complexity of O(n), the lack of pre-computation or optimization makes it less efficient. On the other hand, the optimized approach offers a faster and more elegant solution. Here, the key is to use the provided widths array as a lookup table.
By mapping each character to its corresponding width in constant time, we avoid unnecessary calculations. For example, the width of a character can be directly accessed using the formula width, CA. This insight allows us to streamline the process, improving efficiency while maintaining clarity. The optimized algorithm is straightforward and efficient. First, we initialize two variables, lines, which starts at 1 to represent the first line, and current_width, set to 0 to track the width of the ongoing line. Then, we iterate through each character in the string. For each character, we fetch its width using the lookup array. If adding this width to current_width exceeds the limit of 100 units, we increment the line's variable to account for a new line, and reset current_width to the width of the current character, effectively starting a new line. If the width does not exceed the limit, we simply add it to the current_width and continue. Once all characters are processed, the total number of lines and the width of the last line are returned. This process still has a time complexity of O(n) due to the single pass through the string, but the use of the lookup table eliminates redundant operations, making the solution both cleaner and faster. While alternative approaches, such as pre-computing cumulative widths or using a stack-based simulation, are possible, they tend to add unnecessary complexity without improving efficiency, which makes them less suitable for this problem. The optimized approach is the ideal strategy for this problem. It strikes the right balance between simplicity, efficiency, and alignment with the constraints. By leveraging the widths array as a direct lookup table, we minimize computational overhead while keeping the implementation easy to understand and debug. This is especially valuable for smaller input sizes, like the ones specified in the problem. Comparing this strategy with others, the brute force approach, while also O(n), involves redundant computations that the optimized version eliminates. Alternative methods, such as pre-processing or stack-based simulations, do not improve the overall time complexity and only add unnecessary layers of complexity. Regarding scalability, all approaches handle the problem's constraints well, but the optimized approach remains the most practical and efficient. It ensures the code is both performant and easy to maintain, making it the clear choice for this scenario. The problem we're tackling involves determining how many lines are needed to write a given string, where each character has a predefined width, and each line can hold up to 100 units of width. The input consists of the string S, which is made up of lowercase English letters, and an array widths that maps each letter to its corresponding width. For example, the width of A corresponds to widths 0, B to widths 1, and so on. The challenge is to start a new line whenever adding a character exceeds the 100 unit limit and, at the end, return the total number of lines used along with the width of the last line. To solve this, we initialize the variables lines to 1, since at least one line is always required, and current_width to 0, which will track the width of the current line as we process the string. To calculate the number of lines and the width of the last line, we iterate through the string one character at a time. For each character C, we determine its width using the widths array. This is done by subtracting the ASCII value of A from the ASCII value of C, which gives the index for that character in the widths array. Next, we check if adding the width of this character to current_width would exceed the 100 unit limit for the current line. If it does, we increment the line's variable to start a new line and reset current_width to the width of the current character. Otherwise, we simply add the character's width to current_width. Once all characters have been processed, lines will hold the total number of lines used, and current_width will represent the width of the last line. These values are then returned as a tuple, lines, current_width. This algorithm incorporates several key insights to ensure efficiency. First, the use of the widths array and ASCII values allows for constant time lookup of each character's width, making the calculation very fast. The algorithm also employs a greedy approach, which means it adds characters to the current line until the limit is reached, ensuring that each line is as full as possible without exceeding the 100 unit constraint. Additionally, we handle edge cases such as an empty string, which would result in 1, 0, because no characters are present but at least one line is required. For a single character, the result depends on its width, and if all characters fit within one line, the result is 1 total_width. Finally, when the last character causes an overflow, it starts a new line, and its width becomes the width of the last line. To implement the solution, we rely on simple and efficient data structures.
The widths array provides constant time access to the width of each character, which is crucial for processing the string quickly. Additionally, we use two straightforward variables, lines to count the number of lines and current_width to track the width of the current line. This simplicity keeps the algorithm both fast and easy to understand. In terms of complexity, the time complexity is O(n), where n is the length of the string, as we process each character exactly once. The space complexity is O(1), because we don't use any extra data structures beyond the input and our variables. This makes the solution highly efficient and scalable for larger input sizes. This solution addresses the LeetCode problem number of lines to write string by calculating how many lines are required to write a given string s and the width of the last line, based on the widths of each character.
The function number of lines takes two inputs, widths, a list of integers representing the widths of the 26 lowercase English letters, A, Z, and S, the string to be written.
#### step-by-step explanation.
1. Initialization asterisk. Max_width is set to 100, representing the maximum width allowed per line. Current_width starts at 0 to track the width of the current line.
Lines is initialized to 1 because we begin with the first line. 2. Iterating through the string asterisk. For each character in the string s, the width of the character is determined using widths, ord, char, ord, a. Here, ord, char, gives the ASCII value of the character, and subtracting ord, a, maps it to the correct index in the widths list.
3. Line management asterisk. If adding the current character's width to current_width exceeds max_width, it means the character cannot fit on the current line. In this case,
lines is increment to start a new line.
Current_width is reset to the width of the current character, as it starts the new line. Otherwise, the character's width is added to current_width to continue writing on the same line.
4. Return values asterisk. After processing all characters, the function returns a list containing lines, total number of lines used, and current_width, width of the last line. ### key features. The algorithm processes the string in O(n) time, where n is the length of the string, as each character is handled once. This solution ensures that edge cases, such as an empty string or a string where all characters fit on one line, are handled seamlessly. The function is concise and efficient, making it suitable for production use in solving this problem.
This is the Java implementation for LeetCode problem number 806, number of lines to write string.
The logic mirrors the Python solution, where we calculate the total number of lines and the width of the last line needed to write the given string. Key differences include Java's type declarations, the use of arrays, and iteration over a character array obtained from the string. The solution maintains clarity and adheres to Java conventions while ensuring correctness. To solve this problem, we begin by initializing three variables: max_width, which is set to a value of 100, current_width, which starts at 0, and lines, which is initialized to 1. These variables help us keep track of the maximum width per line, the current width of the line we are building, and the total number of lines we need, respectively.
Now, we process each character in the string s. The first three characters are b, each having a width of 10. As we process these, we progressively add their widths to current_width, which becomes 10, 20, and finally 30. Next, we encounter three C characters, each also having a width of 10. Adding these to current_width brings it to 40, 50, and then 60. At this point, we are still within the max_width limit, so we continue building on the same line.
Moving on, the next three characters are D, each with a width of 10.
Adding these sequentially increases current_width to 70, 80, and then 90. After that, we process the first A, which also has a width of 10, bringing current_width to exactly 100. Now, we encounter another A, but adding its width would exceed the max_width of 100. This means we need to start a new line. We increment lines to 2 and reset current_width to 10 to account for the width of this new A. Finally, we add the last A, which increases current_width to 20. At the end of processing, the total number of lines is 2, and the width of the last line is 20. The final output for this example is 2, 20. Now let's consider an edge case where the string contains only one character.
In this example, the widths of all characters are defined as 4, and the string s contains just the character a. We start by initializing the same three variables. Max_width is 100, current_width is 0, and lines is 1. Since there is only one character to process, we calculate its width, which is 4, and add this to current_width. This gives us a current_width of 4, which is well within the max_width. As there are no more characters, the total number of lines remains 1, and the width of the last line is 4. Therefore, the output for this case is 1, 4. For a longer string with multiple line breaks, let's examine the example where s contains all the letters of the alphabet, and each character has a width of 5. We initialize the variables as usual. Max_width is 100, current_width is 0, and lines is 1. As we process the first 20 characters, from a to t, we add their widths to current_width. Each addition increases current_width by 5, until it reaches exactly 100. When we encounter u, adding its width would exceed the limit, so we start a new line. This increments lines to 2, and we reset current_width to 5 for the width of u. Continuing with the remaining characters, from v to z, we add their widths to current_width, which ultimately becomes 30. The final output for this example is 2, 30, indicating 2 lines and a width of 30 for the second line. To analyze the time complexity of the solution, we start by breaking it down into 3 main parts. First, the initialization of variables such as max_width, current_width, and lines is done in constant time, or O1. This is straightforward since these are simple assignments. Next, we consider the iteration over the string s, which has n characters. For each character, we calculate its width using widths, ord, char, ord, a constant time operation because array lookups in basic arithmetic are O1. We then evaluate whether the current character fits in the current line using an if condition, and update either current_width or the line's counter accordingly. Each of these operations is also O1. Since the loop processes each character exactly once, the total time complexity for this part is O(n). Finally, returning the result, which involves forming a list with 2 integers, is another constant time operation. Combining all these, the overall time complexity of the solution is O(n). Summing up the time complexity, we conclude that the solution runs in O(n), where n is the length of the string s. Now, let's evaluate the space complexity. Starting with input storage, we know the widths array contains 26 integers, 1 for each letter of the alphabet, making its space requirement constant at O(1). The input string s, on the other hand, has n characters, contributing O(n) to the space complexity. For the variables used in the solution, such as max_width, current_width, and lines, each one is a scalar and requires O(1) space. Lastly, the output, which is a list of 2 integers, also takes O(1) space. When we combine these factors, the total space complexity of the solution is O(n), driven primarily by the input string s. When comparing this solution to a naive or brute force approach, we can see significant optimizations. A brute force method might involve explicitly constructing each line as a string or using additional data structures to track line contents. This would increase the space complexity to O(n) for storing all the constructed lines, and potentially complicate the logic. In contrast, the current solution avoids such overhead by maintaining only the essential counters, current_width and lines, achieving O(n) time and O(1) additional space beyond the input size. Looking at best, worst, and average case scenarios, the algorithm remains consistent. In the best case, where all characters fit perfectly within one line, the loop still processes n characters, resulting in O(n) time. In the worst case, where each character exceeds the maximum width individually, the loop still iterates n times, but with additional updates to the line's counter. For the average case, regardless of how the character widths are distributed, the algorithm processes each character exactly once, maintaining an O(n) time complexity. To formally validate the time complexity as O(n), we can rely on mathematical reasoning. Each operation inside the loop executes in O(1) time, and since the loop iterates n times, the total contribution to time complexity is O(n*1), simplifying to O(n). For space complexity, the primary contributors are the input string s and the widths array. While the widths array is fixed at 26 integers, contributing O(1), the string S has n characters, which leads to an O(n) space requirement. Additional variables such as max_width, current_width, and lines only use constant space, and the output itself is a fixed size list of 2 integers, also O(1). Therefore, the overall space complexity is O(n). This efficient design ensures the solution meets the problem constraints effectively, with minimal computational overhead.
When solving this problem, there are several common mistakes to watch out for.
First, not accounting for edge cases, such as when the input string is empty or contains only a single character, can cause runtime errors or incorrect results.
For example, an empty string might lead to accessing invalid indices if not handled properly. Another frequent issue is incorrectly updating the line count.
Some solutions increment the number of lines before confirming that the width constraint has been exceeded, leading to off-by-one errors in the final count. Additionally, confusing the character widths with their ASCII values is a mistake that can result in completely incorrect calculations, as the problem explicitly provides a width array.
Lastly, skipping the width limit check for the last line is another pitfall.
This can generate incorrect results, especially in edge cases where the string's total width is close to the 100-unit limit. Paying attention to these details can help you avoid common errors and improve the accuracy of your solution.
Now, let's discuss inefficiencies and interview strategies.
Inefficient implementations often arise from nested loops or recalculating cumulative widths multiple times, resulting in O(n)² complexity. This approach becomes problematic for larger input sizes, such as strings with more than 10,000 characters. Instead, a linear pass through the string, which ensures O(n) time complexity, is sufficient.
Recognizing key patterns in this problem is also valuable for interviews.
It involves maintaining running totals and managing constraints, similar to scheduling or bin packing problems.
Dynamic programming can also involve related principles.
When optimizing, avoid introducing unnecessary complexity, such as extra data structures, unless explicitly required. Testing edge cases is another critical interview skill. For instance, consider scenarios where all characters have the same width, or strings that align perfectly with the 100-unit line limit. Additionally, remember to test for empty or very short strings to ensure your solution is robust. The concepts in this problem are closely related to several other LeetCode problems. For example, LeetCode 68, text justification, also deals with word wrapping and line constraints, while LeetCode 140, word break 2, explores constraint management while constructing outputs.
Another related problem is LeetCode 1229, meeting scheduler, which involves managing intervals and handling constraints efficiently.
As for alternative approaches, a greedy strategy works well here. By iterating through the string and adding character widths until the limit is exceeded, you can handle the problem efficiently in O(n) time.
This approach is simple and effective. Alternatively, if the width array is used repeatedly for multiple queries, pre-processing cumulative sums can optimize width calculations. While this pre-processing step increases the initial runtime slightly, it allows for constant-time width lookups in subsequent operations, which can be useful in specific scenarios. Finally, let's consider trade-offs between these approaches.
The straightforward greedy strategy is typically sufficient for solving this problem efficiently, as it maintains simplicity and achieves the desired linear time complexity. Pre-processing, while useful for optimizing repeated queries, is rarely necessary in this context, as the problem generally involves only a single pass through the input. Balancing these trade-offs depends on the specific problem requirements, but in most cases, keeping the solution simple and focused on the greedy approach is the best choice. By ensuring clarity and efficiency, you can confidently tackle this problem while avoiding unnecessary complexity.
Great job!
Today, we explored the problem number of lines to write string, reviewed an efficient solution, and discussed its complexity. Remember to practice similar string processing problems to strengthen your skills.
Thanks for tuning in, and we'll see you next time. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!